All right, we're back. Let's do some more E and M, okay? This is Coulomb force and Coulomb's law, the third section of the second unit of physics C notes, okay? You can call it C-02-03, whatever you want, okay? This diagram right here, I'm not really going to do too much with it. I'm just going to show you really quickly that if two charges have an opposite sign from each other, then the Coulomb force, which is the force between any two charges, is going to be attractive, right? You know this, that opposite charges attract each other. Opposite charges attract each other like charges repel each other, okay? So the Coulomb force is an attractive force if the two charges have opposite sign. Notice that we have a positive charge here, and then we have a negative charge on the upper end. So the force is actually going to be attractive, right? They're going to pull each other. They're going to pull each other closer. Okay. If they have a like sign, it's repulsive force. Okay. We got two positive charges here. They're going to repulse each other because they don't want to be near each other. Okay. So just understand that you do need to know the signs of the charges. And then you also need to know protons are positive, electrons are negative, right? That's pretty straightforward, okay? But you do need to know the signs of the charges, particularly to find out which direction the Coulomb force is pulling or pushing, right? Okay. Let's actually start getting into kind of discussing the math and stuff behind it. There's two equations for it that are identical to each other, okay? The first equation is the electric force is equal to K little q big Q over R squared, where the Q's, right, these are just two different charges, okay? Little q and big Q, these are just two different charges. Usually you're given them, you may have to solve for it, okay? But you should know little q, big Q are the two charges that we're trying to find the force between, okay? Another way to express this is the electric force is equal to 1 over 4 pi epsilon naught, okay, Q over R squared, okay? Now, that is a little bit of a confusing way, but these are actually the same thing because, believe it or not, okay, this expression right here, 1 over 4 pi epsilon naught, is actually just K. K is a constant that is this, and epsilon naught is also a constant. So you can either do 1 over 4 pi epsilon naught, that's fine, if you want to memorize that instead, but you have to memorize what epsilon naught is. I think K is easier to memorize though because it has an easier value. It has a much nicer value. So let's pull up the physics C formula sheet really quickly and take a look at it. Okay. You should be given K on here. It should be, here you go, Coulomb's law constant. Okay. It gives you 1 over 4 pi epsilon naught, but it's also 9 times 10 to the 9th newtons times meters squared over Coulomb squared, okay? And then epsilon naught is a variable that represents vacuum permittivity. You'll hear it sometimes be called permittivity of free space, okay? And that's 8.85 times 10 to the negative 12. So obviously 9 times 10 to the 9th is a little bit easier to remember. Okay, I would say try and go for that one, but epsilon naught. Now, here's the part where physics is confusing, if it isn't already confusing enough, right? Vacuum permittivity is not to be confused with vacuum permeability, which is a completely different variable and used for completely different things, okay? So understand that there is permittivity of free space and permeability of free space. Those are two completely different things. We're not using vacuum permeability right now. We will use it later, though, okay? K is 9 times 10 to the 9th, we just talked about, newtons times meters squared per Coulomb squared, okay? And is the Coulomb's law constant. Okay? The value of epsilon naught, we just talked about, is 8.85 times 10 to the negative 12th coulombs squared per newtons times meters squared, right? You notice that the units are flipped on each other, okay? And that makes sense because 4 pi doesn't have units, but epsilon naught does have units, and if you put it in the denominator, it flips to give you this, or it flips to give you that, right? What K is, okay? And it is called the permittivity of free space. Okay? Now, it's very, very important to note that in those diagrams above that I showed you on the previous page, okay, in those diagrams right here, which force, wait, the force, it shows the force is acting on Q, or it shows the force acting on little q, but it's actually acting on both of them, okay? It's not just like that, oh, this one charge has a force acting, has no force acting on it, right? No, they're both going to be pulled towards each other, which means there's a force on both of them, okay? So it's on both charges, and that is upheld by one of Newton's laws, particularly the third. Okay, did you notice, or actually here, we'll talk about elementary charge really quickly, right? We've talked about this before. Elementary charge is the charge of an electron or a proton. Okay, and the value of epsilon, or sorry, value of E is 1.6 times 10 to the negative 19 coulombs, okay? Now, Coulomb's law, if you had a good physics teacher last year, which if you had me, you did, okay, then you will know that Coulomb's law looks kind of familiar, doesn't it? Remember when we talked about gravity and we talked about Newton's law of universal gravitation? Of univ grav. Okay, you remember Newton's law of universal gravitation? Okay. It looks very similar to that. Okay? The only difference is that Coulomb's law lacks a negative. Okay? The reason is because by convention, we typically call attractive forces negative and repulsive forces positive. Electric charges can be negative, but the Coulomb force can be repulsive. Could you imagine if gravity was repulsive? It would not be good for anybody, right? Okay. Let's take a look at this hydrogen atom example, okay? In a hydrogen atom, the proton and electron are separated by about 10 to the negative 10 meters, okay? Calculate the electric force of attraction and the gravitational force of attraction between these two particles. Show your work in the space below. Explain any additional information. Okay, you get the point, right? It's just telling us show our work, right? Okay, well, really quickly, we already know that the electric force, right? We wrote it above earlier, is K little q big Q over R squared, okay? So all we need to do is solve the electric force between a proton and an electron. That would just be the electric force is equal to K, which is 9 times 10 to the 9th, okay? Now, the charge of a proton and electron, right, is the elementary charge. Wait, but the proton and the electron have the same charge, right? So all we would need to do is that little q and big Q would be equal to each other, right? So let's just square it, right? We can do that. 1.6 times 10 to the negative 12th. Yeah, negative 12th, right? Or 19, sorry. I don't know why I wrote 12 in the key. I'll fix that. I have to fix that. 19. It's, you know that my handwriting is bad, right? And so, okay, so 10 to the negative 19th, it is squared, okay? And then we take the distance between the two. Well, it says that they're separated by about 10 to the negative 10 meters. So we'll do 10 to the negative 10 meters squared, okay? You'd have to punch that into your calculator to get a result, but you should get about 2.304 times 10 to the negative 8th. Now, we're now going to use Newton's law of universal gravitation to figure out the gravitational force between the two, right? Because any mass does have a gravitational field. So we can figure that out here, okay? The force of gravity, remember that Newton's law of universal gravitation, G(m)m) over R squared, okay? G is equal to 6.67 times 10 to the negative 11th, okay? Now we need the mass of an electron and the mass of a proton. This is on the formula sheet. It's in the top left right here, okay? This is the mass of a proton, mass of an electron, okay? So we're just going to plug those in right there, okay? 1.67 times 10 to the negative 27th. That's the mass of a proton. Mass of an electron is 9.11 times 10 to the negative 31, okay? And then the distance between the two squared, 10 to the negative 10 squared, okay? And if you calculate that out, you should end up getting 1.01 times 10 to the negative 47th newtons, okay? Now notice there is a massive difference between these two numbers. This is a small number, right? But this is a really small number, okay? Electric force is way stronger. So what does this tell you about the relative strength? Well, we would say that electric force is way stronger. Okay? And to illustrate that for you, I'm not going to write all this again because it's a lot of writing, but this is what that looks like in comparison. Okay? This only has what, 7, 8 if you count the 1 to the left of the decimal point, right? There's 8 zeros there. There are 47 zeros in that one. This is an incredibly small number. This is a small number, but this is a really, really small number, okay? Okay. Hanging balloon activity, again, I mean, we could show this if we wanted to, but it's really hard to get going, and I don't think I would be able to set it up and show it to you here, so I'm going to explain it to you really quickly. Two balloons each have a mass of 0.003 kilograms, suspended from strings of length 1.5 meters. Both are given a charge Q. We can assume that it's the same charge for both balloons, okay? And they're at rest at equilibrium so that the distance from center to center is 0.5 meters. Okay, so let's start labeling things really quickly. The distance from center to center is 0.5 meters. 0.5 meters, okay? That means that half the distance from center to center, so the distance from the middle of the balloon to the center of it, is 0.25 meters, right? Okay, and that is important for us to know. Again, I want you to try this before you actually listen to me go on it, okay? These length L's right here are 1.5 meters, okay? Okay, those length L's are 1.5 meters, okay? We need to draw a free body diagram first and foremost for all of them. This is probably the easiest thing to do, right? So for the left balloon, we should have gravity going down, okay? We should have the electric force pulling to the left, okay? I swear I heard something, which is weird because it's Sunday. There shouldn't be anybody at the school. Okay. You have the electric force pulling to the left, okay? And then you should have a tension force from the string going up and to the right, right? 1, 2, 3, 1, 2, 3. So we'll go about that, like that, okay? Okay. And then you have a vertical and a horizontal component to that tension force, okay? So you have a vertical component and a horizontal component. This is Ftx, Fty, okay? This one right here, same thing, but actually mirrored image. So it's going to have gravitational force going down, 1, 2, 3. And then force to the right, 1, 2, 3. Okay, and then the tension force goes up and to the left this time instead of going up and to the right. So it would go 1, 2, 3, 1, 2, 3. Okay, and again, a vertical component and a horizontal component. Okay. Okay. You should know that if they're at equilibrium, which I believe it says, yeah, it says right here at equilibrium. Okay. They're at rest at equilibrium. That means all the forces balance, which means that the left forces must equal the right. And the up forces must equal the down. Okay? Okay, now when you have this, okay, that means everything has to balance each other out. So if we set the left and the right forces equal to each other, it doesn't matter which one you pick, right? Because it's going to be the same thing. You'll notice that the electric force should be equal to the x component of the tension, okay? And then the up forces and the down forces, you should notice that F sub g, gravitational force, should be equal to the y component of the tension, okay? And if we're given this angle up here, which we are in the problem, okay? Or we're not given the angle, right? But we can figure, but there is an angle there, right? If we're given that angle there, well then x is the opposite of that, and so we would say that we could use the the sine for the x component and the cosine for the y component, right? Okay, so we're given that angle. It doesn't matter which way you do it. You would use sine for the x component and cosine for the y component, okay? So right here, f sub e equals ftx. If we expanded it out, you would get kq squared over r. And the reason we're able to square q is because the charges are the same, okay? It equals ft sine theta, okay? Then on the right side, so up equals down, you would get mg is equal to ft cosine theta, okay? Now, in an effort to solve this equation, right, because the unknown that we're looking for is the, we're looking for the charge ultimately, right? In order to solve this equation, the easiest way to do it is actually going to be to put one of them on top of the other, okay, and divide them out. And we can do that. So let me show you how that would look. If we put one on top of the other, we would get ft sine theta over ft cosine theta equals kq squared over r squared over mg. And this makes things a lot easier because now we don't need to know what the tension is in the strings, okay? But also on top of that, you'll notice we have sine over cosine, which is tangent, okay? kq squared over r squared over mg. Now here's the thing. We don't know what theta is, okay? We haven't solved for theta, okay? We will need it, right? But the way that we can actually get theta is pretty simple, right? Because what we've done up here is we figured out the base, or this leg of the triangle, and the hypotenuse, okay? We figured out what's opposite this, and then the hypotenuse, okay? So what we can do is we can use the Pythagorean theorem to figure out what that angle is, okay? And to get it should be the tangent, should be, so let's see, we've got the opposite and the hypotenuse. That would be sine, right? So we would say that the sine of theta is equal to opposite, which is 0.25 over 1.5, right? Okay. Yeah, sorry, you can't see that from the frame, right? It should be the sine, right? Because it's the opposite and the hypotenuse, right? Okay, so then the sine of it equals 0.25, and then 1.5. And then in order to get theta, we would need to do the inverse sine of both sides. So you should get sine inverse of 0.25 over 1.5. And you should end up getting about, what was it? It should be about 9.8 degrees, I believe it was. Let me double check. Okay, let me get my calculator because I just realized I don't actually have it in the key. I guess I didn't write down how to find the angle there. Okay. So you should get sine of equal to, let me make sure I'm in degree mode. There we go. Okay. 0.25, 1.5, and you should get, yeah, about 9.6, okay? About 9.6 is fine, okay? I think when I did it, I got a slightly different angle. It might have just been how I calculated it, okay? But you should get about 9.6, okay? So theta should be equal to about 9.6, okay? Okay, degrees, okay? So then what you're going to do is you're then going to solve for Q in this equation that I have here in the orange, okay? Can't really see it that well, so I'll turn on the light. I don't think that's actually going to help any, okay? And in order to get this all by itself, okay, what the easiest thing to do is going to be is you'll need to, this is the same thing, right, as saying tangent theta equals kq squared over r squared mg, right? Because the r would just go into the denominator, okay? So you would need to multiply by r squared times mg, okay? Or sorry, yeah, multiply by r squared times mg on both sides and then divide by k. and then take the square root, right? So you should end up getting, if I'm going to skip a couple steps here because you should be working this out, but it should be about, you should end up getting that q squared is equal to mg r squared tan theta over 9.10, or sorry, 9 times 10 to the 9th, okay? Because that's k, right? I don't know why I actually substituted k in there, okay? I'm clearly not it's Sunday, right? Give me a break, okay? And then when you calculate that out, you plug everything in, and then you would take the square root of it, okay? You would end up finding that the net charge should be somewhere in the ballpark of about 3.7 times 10 to the negative 7th coulombs. Now, again, that's going to depend on if you got 9.6 or 9.8 for your angle. You can get it either way, okay? But it should be in the ballpark of that. That's what we're going to use going forward, okay? To figure out the number of excess electrons, right? Well, this is our net charge, which means this is the charge that we essentially have in excess, okay? Then you would just divide net charge by elementary charge. Because your net charge should be some multiple of electrons, right? So if you divide the net charge by the elementary charge, okay, we set that up, 3.7 times 10 to the negative 7th. You divide it by the elementary charge, 1.6 times 10 to the negative 19, okay? You should get about 2.3 times 10 to the 12th, okay? 2.3 times 10 to the 12th, okay? Not negative 12th, 12th, okay? Electrons, okay? Okay, in rubber materials, there's 1 electron for every 3 times 10 to the negative 27th kilograms of mass in the substance. So how many electrons should there be in a neutral balloon? If the balloon is neutral, okay, then you would take the total mass of the balloon, and if you know that there's going to be 3.0 times 10 to the negative 20, or sorry, and if you know for every kilogram, every 3.0 times 10 to the negative 27th kilogram, there's 1 electron, you would just take the mass and divide it by that, right? So you would take the total mass of the balloon, which I think we're given is 0.003, okay? Okay, divided by the mass per electron, or the electrons per that mass, right? So this would be 3.0 times 10 to the negative 27th, right? Because if there's 1 electron every 3.0 times 10 to the negative 27th, just divide 0.003 to figure out how many times this fits into that, okay? And you should end up getting about 1 times 10 to the 24th electrons, okay? So it's a lot of electrons. To put that to put it comparatively, right? The number of electrons in a neutral balloon are this much, okay? Okay, you draw those zeros all the way out there. The number of excess electrons that we had in the previous in the first example, or in the initial example, is approximately this much right here. And you would go on and on and on, right? Okay. So a lot of electrons in a neutral balloon, okay, and then we have that many, this many electrons in excess, okay. So we have all those electrons in the first one, and then the extra one, those other ones in excess. Okay, that's the end of this example right here, and the end of this section. Okay, all right. Have fun. Stay cool.